In some cases, you wanted to have a wall like that. There is no signal that the wall should be closed. There is another wall which is referred as fail close. So here you can see if this particular signal fails, in that case, this particular flux will go up and the wall will be closed. This is fail close. Okay. So in the next semester, you are going to do a experiment on wall characteristics, isn't it? So these are the different types of plugs which are used in the wall, and depending on the geometry of the plug, the characteristic of the wall varies, isn't it? So in this case, you can see that the flow rate coming out from the wall is given as K f of x under root of delta P by rho, where delta P is nothing but the pressure drop across the wall. Rho is the density of the fluid. F of x, this particular term is coming from the characteristics of the wall, and K is the constant which depends on the size of the wall. Okay. So in this case, you can see that this f of x, we can get this f of x depending on what type of wall we are looking at. So there are different types of walls are there, and depending on the geometry of the plug, the type of the wall is defined here. For instance, we can have a square root, linear, equal percentage, hyperbolic, quick opening, and depending on the type of plug is being used, this f of x is going to vary differentially. Okay. So in this case, you can see that in a linear case, you can see that this f of x is given as just x, where x is what? X is nothing but a stem position. X is a stem position. Okay. The stem is moving. Remember. So what is the stem position? That is defined by this x. So when f of x is given as x, then the particular wall is referred as linear. In this case, the wall characteristic curve is a straight line based on 0. Okay. Similarly, for quick opening, the plug is like this. Isn't it? So for a quick opening, this is the characteristic you get. For a square root type of a wall, you get this characteristic. For equal percentage, the other characteristics. So depending on what type of plug you are using, characteristics of the wall is going to vary. And this particular experiment you are going to do in the next semester. There are 3 types of walls present in the lab. Okay. I think quick opening, linear, and equal percentage. So these are the 3 types of walls which you have to evaluate next semester. Okay. Once you get this f of x, you put it in this particular equation, and you can find out the flow rate coming out from the wall. So flow rate coming out from the wall depends on the size of the wall, which is this parameter k depends on the size of the wall. Whereas the f of x is coming from this wall characteristics, and delta P by rho, this is the pressure drop across the wall. Okay? Alright, is it clear to everyone? Okay. Now let's move to a important topic, which is feedback control system. Feedback control system, we have already seen feedback control system. So whenever there is a disturbance coming into the system, that disturbance is going to impact the output variable. This impact we are going to measure, and depending on how much it impacted, we are going to perform the corrective action. Isn't it? So action here is dependent on how much my system is messed up. Isn't it? So you can see that the impact of the disturbance is first felt on the system, and then you are active on it. And that is the reason why it is called as feedback. Okay. So in a feedback system, typically these are the elements. You can see this is the process where the disturbances are coming in regularly. Isn't it? This is the process where the disturbances are coming in regularly. And also there is a input manipulated variable. Isn't it? So whenever the disturbances are coming into the system, I am interested in manipulating this manipulated variable such that the impact of this change in the disturbance is not going to be there in my output variable y. So that is what the final aim is, isn't it? So how do we do that? First, so see in this case, whenever there is a change in d, it is going to impact y. So the first step is what? I have to measure y, isn't it? So that is why y is measured here by measuring device. So first you are measuring y, isn't it? Once you have measured the y, remember this measured value of y may not be same as y, because its measurement unit will also have its dynamic. isn't it? And therefore this ym which you are getting may not be exactly same as y. Okay. So whatever y you have measured here ym, this ym then you are going to compare with the set point value. So that is what you are doing here. You are comparing it with the set point value. So set point value is ysp. And ysp, this will have a plus sign, this will have a minus sign. So ysp minus ym will give you error. And that error which we have obtained here at a comparator will be given as an input to the controller. And controller, depending on the value of the error, is going to give you the output signal, which is called as actuating signal in this case. This actuating signal is given to the final control element. So this actuating signal will be an electronic signal or a pneumatic signal in order to open or close the valve. Okay. So depending on this particular signal, this particular last element, which is a final control element, is going to open or close, isn't it? And how much I should open, how much I should close, that will also be governed by the strength of the signal C. Correct? Is it clear to everyone? And once the valve is open, it is going to change the flow rate, isn't it? And that flow rate is given to the system. So this m is nothing but manipulated variable. So this manipulated variable is modulated by a final control element. So this is the typical feedback system. Is it clear to everyone? Correct. Now this entire system we have represented in a block diagram where individual elements are represented by its transfer function, isn't it? So in this case, this is the process. So process will have how many transfer functions process will have? Process will have two transfer functions. Remember in this case, how many input variables are there? D and M, isn't it? So whenever there is a change in D, how that change in D is going to impact my Y? It will have one transfer function. Remember what is the definition of the transfer function? Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form. So here there are two inputs and one output. How many transfer functions we are expected to get? Two transfer functions we are expected to get. So the transfer function relating D and Y is represented as GD. Is represented by GD. Whereas how this M is impacting Y. The transfer function relating how Y is changing when there is a change in M, this particular transfer function is given by GP. So GP and GD, these both are the transfer function of the process, isn't it? Associated with the individual variable. So this GD is a transfer function of the process associated with the disturbance variable, whereas GP is the transfer function of the process associated with the manipulated variable. Is it clear to everyone? So this entire block which is shown by a shaded color here is a process. Isn't it? This entire shaded block is a process, isn't it? Now this process, remember this particular transfer function is associated with the manipulated variable, but manipulated variable is coming from where? It is coming from the final control element. So before this manipulated variable here, I should have a transfer function of the final control element. So that is why GF is put here. So GF here is nothing but the transfer function of the final control element, which could be a recurring pump or valve. Correct. Now to this final control element, the signal is given by controller. So I should have a controller before this. So therefore the transfer function of the controller is coming in here. So GCS is the transfer function of the controller. This controller is given as an input, which is the error epsilon s. This epsilon s is coming from where? By comparing the set point and the measured value of the signal. So here I will have YSP plus sign, YMS here negative sign. So YSP minus YM, that gives me E of S. Isn't it? Correct. And this YM is coming from what? It is coming from measurement unit. Isn't it? So I will have a transfer function of the measurement unit here. So you can see that YS is given as an input to the measurement unit. That will give me YM. This YM is compared with the YSP. That gives me error. Error is given to the controller. Controller based on the error gives me the actuating signal. Actuating signal is given to the final control element, and final control element gives me the manipulated variable, isn't it? And this manipulated variable is then given to the process. Okay. So this is the feedback control system represented in a block diagram. I have shown everything in a S domain. This entire block diagram is represented in a S domain. Okay. Remember, in this case, all these are function of S. Okay. Is it clear to everyone? Yes. No. Is there any confusion that side? C or there is a big question. What is M? M is the flow rate. And what is the output coming from the controller? It is electronic signal. वो current आ रहा है वहाँ से. That current is given to a wall, and wall is going to open, and based on that the M will be there, isn't it? Okay. So in this case, this signal C of S is actually a current, or if not, then it's a pressure. If it's a pneumatic valve which you are looking at, in that case this will be a pressure signal. If you are looking at this as an electronic, let's say there is a valve and on the top of the valve there is a stepper motor. Usually you have a stepper motor. So stepper motor has around 360 markings. Depending on what signal you are giving, it is going to open from 0 to 360 degrees. Okay. Clear? Is it clear to everyone? Yes, no. If you are not clear here, I am damn sure after this nothing will be clear to you. Because this is the starting point. After this we are going to make our analysis more and more complex after this. So please let us know if something is not clear. Okay. So this entire block diagram can be simplified. We will see the simplification. In fact, some of you might have seen the simplification in the tutorial class. Okay. We can simplify this entire block diagram. Okay. And we are going to derive the simplification, and then we are going to formulate the rules. Okay. So in this case, this entire block diagram can be simplified like this. Where remember, in this case, this M of S is the input, isn't it? But this M of S is actually dependent on C of S. This C of S is dependent on E of S, and this E of S is dependent on Y of C. So in this entire block diagram, what are the input actually? In the process, the input is B and M. But if you are looking at this entire feedback loop, the input is what? Input is disturbance variable which you do not have any control, and the second input is a set point, YSC. Isn't it? So these are the two input given to the feedback system. Okay. Now with respect to each of these input, I can have two transfer functions. Remember, this is what we have seen when we started initially. Remember, depending on how many output variable and how many input variable, you will have the number of transfer functions. If you have two output variable and two input variable, how many transfer functions are expected? 4. In this case, only one output variable is there, but there are two input variables, D of S and Y of S. So how many transfer functions you are expected to get? 2. And whenever you are looking at the transfer function which is relating D of S and Y of S, that will be represented as G load. Okay. And this G load will not be same as GD. Why? Because now you are accounting this entire loop. So this G load is going to be different than this GD. We will see that. We will do the entire derivation in detail. Okay. Similarly, there will be one more transfer function which is relating YS with YSPS. Isn't it? And that transfer function is given as GSP. Okay. So GSP is nothing but the transfer function of a servo problem. That is why this SP subscript is used here. This SP stands for servo problem. What is servo problem? We will again come back. Don't worry. And this G load is nothing but the transfer function of a regulatory problem. Regulatory problem is the problem in which only the disturbance variable is changing. Okay. and the servo problem is the problem in which only the set point is changing. So in a way, the servo problem is nothing but set point tracking problem, whereas regulatory problem is nothing but what? Regulatory problem is nothing but negation of negating the disturbance. Regulatory problem is nothing but negating the disturbance, whereas servo problem is nothing but tracking the set point trajectory, set point. Okay, is it clear to everyone? Okay, now let's look at the entire derivation little bit in more detail. What we are interested in? भैया कहाँ? Where you have been? कहाँ टाइम क्या हो रहा है? 10:23 आप बोल रहे थे मैं खुद हॉस्टल में आता था आपके अटेंडेंस देखते हैं. Why you required to come here? No, you why you are running? सुन के जाओ. हाँ, थोड़ा सा सुन के भी तो जाओ. आप तो एकदम पतली गली से पीछे से निकलते जा रहे हो जैसे as if nothing happened. जब कोई प्रॉब्लम है तो मुझे बुला लेते हैं, मैं आ जाता हूँ. साइन ही तो करना है, तो जाते जाते मैं ले आ जाता अटेंडेंस. वही साइन करा देते हैं आप. Why you required to come here? Tell me. If the attendance is the only thing you are caring for, then you tell me. आजकल मुझे भी थोड़ा सा वेट कम करना है तो मैं आ जाऊंगा वॉक करते हुए आपके पास. ठीक है, चलेगा क्या? चलेगा या नहीं चलेगा? नहीं चलेगा ना, तो फिर टाइम से आया करो. ठीक बात है. और इधर सामने बैठो. चलो आओ इधर आओ. पार्टी से बैठो. इधर आओ. वहां नहीं, इधर यहाँ अटेंडेंस आ जाएगी. अटेंडेंस का टेंशन ना लो, मैं आ जाऊंगा लेके अटेंडेंस. Why you are worried? Okay, so where we are? So why is the output? Why is the output? We are interested in how this y is changing whenever there is a change in yst and when there is a change in d. All the variables are taken in a deviation form. You can see that y dash is taken here, d dash is there, yst dash. All these variables are in a deviation form. Remember in the earlier case also all these variables in deviation form. I have omitted that dash. Remember in the starting class itself I said all the variables are in deviation form unless it is specified. Okay. So in this case all these variables are in a deviation form. Let's look at how this y we can obtain. So y dash is given as this gb into d plus m dash into gb. Isn't it? M dash into gb plus this plus sign here plus d dash into gd, that will give me y. Y dash. Yes or no? Is it clear or no? Clear. So then m dash we can represent. M dash is the output from this final control element. So m dash can be represented as c dash into df. Isn't it? So this m dash I can represent as c dash into df. Similarly, this c dash is the output from the controller. So that can be represented as epsilon into gc. Isn't it? So I can keep on replacing the variable till I reach this point. Once I reach this point, epsilon is nothing but what? Yst minus ym. And again here the ym is nothing but what? Y dash into dm. If you put that entire thing, what you are going to get? These are the same things I have written here. If you do that, what you are going to get is this equation. See, y dash s is given as gps ms plus gds ds. Here this m dash s is replaced by gfs gcs ysps minus yms. Isn't it? And this yms also we have replaced. This yms we have replaced by y dash into gms. Remember in this case this y dash into gms is yms. So that is what we have replaced here. Now this entire equation, if you look at this entire equation, there is a y dashes here and y dashes here, both. I have to collect both these y dashes. If I collect both these y dashes and rearrange the term, what I get is this entire. So see this y dashes, I can take it on this side, so this entire term will be 1 plus this. And this 1 plus this entire multiplication of all transfer functions comes into the denominator. Okay, is it clear? Yes, no? This looks like this S in a superscript. This is a typo here. It's not a superscript. It's Y dash S. Okay? It's Y dash. Is it clear to everyone? Now look at this particular equation. What this equation is giving me? What this equation is giving me? Look at this particular first part here. Y dash S. How this Y dash S is related to YSP dash S? Whenever there is a change in the set point, based on that, how my Y dash is going to change, that is governed by this first part. Isn't it? And the second part, whenever there is a change in the disturbance variable, how my Y dash is going to vary, that is governed by the second part. Isn't it? Correct. It may possible that you might be having both YSP dash and D dash, both are non-zero in your actual problem. Isn't it? It's not necessary that you will have only one problem at a time. Remember, when you are having only YSP dash and this let's say this D dash is 0. Remember, all these variables are given in a deviation form. So if there is no change in the disturbance variable and only change in the set point is happening, in that case this entire term is going to become 0. Yes or no? Similarly, if there is no change in the set point and only the D dash is going to change, in that case this first term is going to become 0 and only the second problem will be there. Second part will be there. Isn't it? So when this part is 0, then the problem is referred as servo problem. Why? Because you are only tracking the set point. When this first part is 0 and only the second part is present, then we call it as a regulatory problem. Why? Because you are now only negating the disturbance. Only negating the disturbance present in the load variable. Okay? But it is not necessary that only one of these are present. It may be possible that both are simultaneously present. Okay? Is it clear to everyone? Now this particular part, this entire term is nothing but GSP. The GSP which we have shown here, this entire term is the GSP. Remember, YSP multiplied by GSP gives me YS. So that is what is here. See, YSP multiplied by this entire term which is GSP gives me YS. So this entire term is YS, GSP, transfer function of the servo problem. Similarly, this entire term is nothing but the transfer function of the regulatory problem. So this is nothing but G load, which is given here. This G load. So G load into DS plus YSP into GSP gives me YS. So that is what you are going to get. GSP into YS plus G load multiplied by DS. That gives me Y. Is it clear to everyone? Simplification is clear. Now look at this equation slightly more detailed way. Now what is happening here? What is numerator? What is numerator here? So see, this is the input. If you are looking at the servo problem is what? This is the output, this is the input. So between output and input, this is the output and this is the input. Between this output and input, what are the transfer functions in the forward line? The transfer functions in the forward line are GC, GF and GP. So only these transfer functions are appearing in the numerator. Isn't it? So all the transfer functions which are there in the forward line will appear in the numerator. Whereas all the transfer functions present in this entire loop means what? GC, GF, GP as well as GF. Multiplication of all these transfer functions in the loop plus 1, that will appear in the denominator. And this particular rule is not only true for this first part, this is also true for the second part. Look at the second part. This is the input, this is the output. So between the input and output, what are the transfer functions in the forward line? Only GD is there. So GD is appearing in the numerator. And in the denominator again 1 plus the transfer function of the entire loop. Is it clear? So this is the rule. Okay. Whenever you wanted to simplify such complex feedback loop, this is the rule you have to follow. Numerator becomes transfer functions in the forward line, all the transfer functions in the forward line, divided by 1 plus all the transfer functions present in the loop. That is what is going to give you a transfer function of the transfer function between the input and output whenever you are having a feedback loop. Now one more important thing to note down here. this particular rule is valid only when we are having a negative feedback. What is negative feedback? What is negative feedback? Remember, whatever the measured value is there, that we are subtracting here. So minus sign is here. So whenever I have a minus sign here, then it is referred as negative feedback. It is not necessary that you will always have a negative feedback. In some cases, you can have a positive feedback also. Let's say this minus sign, if I change to a plus sign, then instead of 1 plus, I get 1 minus. In that case, I get 1 minus here. Okay, so please note that this 1 plus, this multiplication of all the transfer function in the feedback loop, this particular rule is valid only and only when you are having a negative feedback. When you are having a positive feedback, instead of plus here, you will have a minus. Is it clear to everyone? Yes, no?
Yes.
Okay, so the same thing is written here. So this is the transfer function. I can represent this part as GSP. This part we can represent as G load, isn't it? GSP and G load are the transfer functions of the servo and regulatory problem. In a servo problem, GDS is 0, so there is no disturbance occurring. Only the set point change is there. So in that case, this Y dash S becomes GSPS, YSPS. That's it. So this entire term becomes 0. So only you will have Y dash S into Y dash S will be given as GSPS into YSP dash S. That's it. And in the regulatory problem, GSPS is 0, so there is no change in the set point, only the GD is changing. So in that case, Y dash S is given as 0 dash into D dash S. Again, the denominator is given as 1 plus multiplication of all the transfer functions in the entire loop. Numerator is the product of all transfer functions in the forward line. Correct? Okay. Now let's look at one simple example. Now this tank example we have seen several times, isn't it? The concept is clear, feedback. Now let's see how this feedback concept of feedback we can apply to a tank system. Now in this case the tank is given where the inlet is Fi, outlet is F0. I am interested in maintaining the height of the liquid present in the tank. Okay, so I am interested in maintaining the height of the liquid present in the tank. So my output variable in this case is what? Output variable is H. Isn't it? The inlet in this case is what? Inlet is Fi as well as manipulated variable is F0. Okay, manipulated variable is F0. Now in this particular case, what we are doing? The outlet flow rate we are modulating. So we are measuring the height. We are measuring the height by using differential pressure state. And this measured height then we are comparing with the set point of the height. That gives me the error. Error is given to the controller. So controller is going to give me the electronic signal C, and depending on the strength of this signal C, this valve is going to open or close. And depending on that, the flow rate F0 is going to vary. Clear? Now this entire system I can represent as a feedback system like this. Okay. We will look at each of these elements again one more. I will come back to this thing. Now what is the process here? Process is A dH by dt is given as Fi minus F. Fi minus F0 actually, I omitted that. F0 is should be here instead of F. Is that it? So there is a typo. This should be Fi minus F0. Okay? Now, in this particular case, if I apply the Laplace transform, what I will do? If I apply the Laplace transform, I will get H dash S, Hs into S. Derivative is there, so Hs into S. So that S I can take it out, so that becomes AS. Isn't it? So that AS, if I take it on the right hand side, I am going to get Hs is given as 1 by AS Fi dash S minus 1 by AS F0 S. Do you all agree with me? Is it clear to everyone? So now you can see that what is Fi is here? FIS is here input, and what is F0 is the manipulated variable. Output is HS, isn't it? So the transfer function associated with the input is referred as the transfer function associated with the disturbance variable. Remember, this is the disturbance variable. The transfer function associated with the disturbance variable is represented by what? It is represented by GD. It is represented by GD. I can go back. See, the transfer function associated with the disturbance variable is GD. Similarly, the transfer function associated with the manipulated variable is GP. So in this case, this is the disturbance variable. So the transfer function associated with this disturbance variable is what? 1 by AS, which is nothing but GD. Whereas F0S is the manipulated variable. So this 1 by AS is nothing but GP. Correct? I am in the class. Call back to you. Okay. So now this 1 by AS is okay, so this is 1 by AS is GD, and this is 1 by AS is GP. So that is what we have represented. Remember, in this case GD is given as 1 by AS and this GP is given as 1 by AS. But you can see that this 1 by AS is associated with the minus sign. That is why minus sign is coming here. Whereas there is a plus sign associated with this, so that is why a plus sign is coming here. So this entire thing is represented here as a process. Do you all agree? Is it clear to everyone why we are representing like this? Now let's look at, okay, differential pressure cell. What is differential pressure cell? Differential pressure cell is what? Anyone? It's a manometer. It's a manometer, isn't it? And manometer transfer function we have derived. Manometer gives us what? It gives us second order transfer function. So that is why differential pressure cell we have represented as a second order equation. It is going to be a second order transfer. Okay. Again, one more thing to note down. Actually, it is given as Kp into delta P, where delta P is nothing but the pressure drop. But I am interested in what? I am interested in height. Height and delta P, these are related by what? H is represented as under root of delta P actually. But in this case, we are taking it as a proportion. Why? Because we don't want it to be non-linear. Delta B is under play, isn't it? So we don't want it to have non-linearity. That is why the proportionality we have taken. So in this case, this delta P we have represented as Kp alpha into. So you can linearize it. I don't want it to go into that one more step of linearization, isn't it? Okay, is it clear to everyone? So in this case you can see that the measured value of the height, how that is going to related with the actual height will be a second order term. So in this case you can see that this height h, which is the actual height, is measured by a differential pressure cell, and this is the measured height. So what will be the measured height when there is an input, which is the actual height will be governed by a second order term. Okay, this measured height then is compared with the set point. So HSP minus HM will give me the error epsilon s, and this epsilon s is given to a, let's say in this case we are using a PI controller. So PI controller will have a transfer function Kc into 1 plus 1 upon tau is. So that is why this GC is represented as Kc 1 plus 1 upon tau is. And whatever the signal coming from this controller, electronic signal it will give, that electronic signal will be given to the wall. isn't it? Wall. Typically, we ignore the dynamics of the wall, isn't it? But let's say if you wanted to include the dynamics of the wall, in that case, we can take a first order system for a wall, and that is the reason this final control element is represented as kV divided by tau v s plus 1. So here you can see that the tau v is nothing but time constant of the wall. In this case, this tau is nothing but the time constant of the differential pressure cell, isn't it? And this tau I is nothing but the integral time. Okay, is it clear to everyone? Yes, no? How we have represented this entire block diagram?
So what is that?
In a final control element. So in this case, we are representing the first order process system. So in this case, the input will So in this case, the input will be the electronic signal. Remember, there is a wall, and on the top of the wall there is a stepper motor. Isn't it? So electronic signal came to the stepper motor, and depending on this electronic signal, the wall is going to open. How much this wall is going to open when there is a electronic signal coming in? The relationship between these two will be a function. Okay. So actually, in a time domain, what we are going to get is, if there is a step input, in that case you are going to get a kp1 minus e raised to the power minus t by tau v. That is what you are going to get. Typically, the dynamics of the final control element is fast. So we usually take GF equals to just kV. We usually take GF equals to kV. So what it means is, your wall is going to reach to the ultimate value very fast. So then it becomes just kV. Remember, what is the ultimate value of the wall? Just kV you are going to get, isn't it? Is it clear to everyone? There are small details are there. Unless and until you work out, you are going to miss this detail. I am telling you this again and again. I remember this because I have done this several times. That is why I am able to remember. Remember, I told you that this course I used to teach on blackboard earlier. So I taught this course on blackboard almost 5 to 6 times. Only the last year I have made those lines. Okay. So there are small details. Unless you practice yourself, you are going to miss. Don't be a wrong impression that you can do it on the last day, on the day of the quiz or minor. It is not going to happen. That program you might have learned by now. Isn't it? Okay. So please go through. Everything is available with you. But then it's a disadvantage sometimes. Everything is available with you means you have to find out from that. Isn't it? And very often it is not at all there. That is the problem. Okay. But if you do that carefully, whatever even the new thing is there, you will be able to do it. That is what I have seen. Okay. I will not give anything which is very far away from what we are doing. It will be slightly away from what we are doing. Okay. Alright. So where we are? Now a similar example is taken for a. Not interested? Should we stop here? We have a lot of syllabus to cover, by the way. We have not even reached to stability. Let's do this example and then do it. Okay. So this particular example is again the same stud and hitter example we are looking at. Here there is a input is F and Ti. We are assuming only the disturbance Ti. My aim is to maintain the temperature T inside this cavity. Isn't it? Manipulated variable here is the steam flow. Okay. Now balance equation given here is V dt by dt is given as Fi Ti minus C plus Q by rho C. Here this Q is nothing but what? Let's assume that the saturated steam is flowing through the jacket. So if the saturated steam is flowing through the jacket, the heat supply will be given by lambda into FFC, where lambda is the latent heat of vaporization. Okay. So this Q can be replaced as lambda into FFC, so we will get this equation. I can rearrange this equation. So after rearranging, we get the equation like this, where V by Fi we can represent by a time constant tau. So we get a first order equation like this, tau into dt by dt plus C equals to Ti plus K FSC, where Ti is the disturbance variable, FSC is the manipulator. Okay, again I can take the Laplace transform from this entire thing, and what we get is the output variable Ts in a Laplace domain is given as 1 upon tau s plus 1 Tis plus K by tau s plus 1 FSCs. Now this transfer function here, this transfer function is associated with disturbance variable. Remember here Ti is the disturbance variable. So this transfer function is associated with the disturbance variable. So this is nothing but what? This is nothing but GD. Similarly, this transfer function is associated with the manipulated variable. So this is nothing but GP. And now I can use the same block diagram of the feedback loop to put GD and GP there. Again, in this case, the temperature is measured by thermocouple. Thermocouple is first order dynamics. Remember, temperature measurement is most of the time first order. Okay, so that is given by first order transfer functions. If the thermocouple is fast, in that case just give kmts. If it is not fast, in that case you will have km divided by tau ms plus 1. First order dynamics, isn't it? Similarly, let's say the proportional controller is being used. In that case, the transfer function of the controller is given as k into epsilon. And the final control element, let's assume that the first order transfer function that becomes kb divided by tau s plus 1. If we rearrange this entire thing in a feedback loop, our feedback loop looks like this, isn't it? So Ti is associated with 1 upon tau s plus 1. FSC is associated with k divided by tau s plus 1. Both these signals are added, that gives you Ts. Again, this FSC coming from the final control element, so that is GF is given as kV divided by tau Bs plus 1. GC equals to KC. Why? Because we are using only a proportional controller. Let's say if we are having here PID controller. In that case, what this would have been? KC 1 plus 1 upon tau Is plus tau Ds. That would have been the transfer function. In this case, it is a proportional controller. That's why it is just KC. And here, the thermocouple we are using, we are assuming that the thermocouple dynamic is going to be very fast compared to the dynamic of the process, and therefore the dynamic of the measurement unit is ignored. And that is the reason why we have taken Gm equals to Km. Typically, if you don't know anything, in that case it is first order. Km divided by tau ms plus 1. Okay. So with that, this is the expression we are going to get. Here you can see that the output temperature is given as GSP, TSPS plus G load into TIS. GSP is what? Transfer function of the servo problem. How we can obtain? So GSP is nothing but the transfer function between TS and TSPS. That we can obtain as all the transfer function in the forward line divided by 1 plus transfer function of the entire loop. That is what is calculated. See, KC kV by tau s plus 1 into k by tau s plus 1 divided by 1 plus kc into kV divided by tau s plus 1 into k divided by tau s plus 1 into km. Similarly, for a regulatory problem, G load is nothing but what? Nothing but the transfer function between TS and TIS. In that case, the numerator will be just GD, isn't it? So that becomes 1 upon tau s plus 1 divided by this entire denominator. Correct? So we will stop here and we will continue from this one. There is a lot of derivations is there. So we have just started. Okay, so please go through. Things are going to become more and more complex now onwards. Please go through the material. So we have a class on Friday. आओगे तुम तो फिर आर्टिस्ट में चले जाओ आओगे ना कहाँ तक पढ़ाएंगे मैक्सिमम यहाँ तक कंप्लीट करना है
अडेप्टिबिलिटी ठीक है
यहाँ तक हमें कंप्लीट करना है आई एम नॉट श्योर हाउ मच यू विल बी एबल टू डू
मतलब यहाँ तक लेकिन
यहाँ तक सिलेबस आपके गेट में गेट में यहाँ तक सिलेबस है वो आई एम इंटेंडेड टू कंप्लीट एट दिस
घर में एडमिट हो रहे हैं, तो जो बचे हुए दिन होंगे, अगर 14-15 दिन तक बेड रख जाएगा वो मल्टीपल सर्जरी का, तो उसमें क्या मेडिकल से अटेंडेंस लगती है। हाँ,
कितने मैक्सिमम क्लासेस अटेंड कर सकते हो सर?
ये तो 100% है।
100% है ना, तो फिर कोई दिक्कत नहीं।
3 दिन क्लास छुट्टी से 75% है।
Thank you.